So our summit presentation is on AI and water conservation.
All right, so there are a few problems. According to the Southwest Climate Center workshop, partnership with the United States Geological Survey and the U of A, Arizona has been in some stage of drought for the last 30 years. Drought is defined as a prolonged period of abnormally low rainfall weather leading to a shortage of water by Merriam-Webster. Droughts are exacerbated by climate change, especially as its role on altering weather events to be fewer and farther between, punctuated by times of extreme, increasingly destructive storms, as seen by the National Oceanic and Atmospheric Organization, through not just droughts, but also hurricanes, wildfires, and flash flooding throughout the world. Rainfall and this specific problem of drought conditions specifically relates to Arizona, as the Phoenix metropolitan area is located within a desert, and with a rapidly growing population of about 5 million people, is the largest such in the United States. These 5 million people need access to water, 100 gallons a day according to the United States Geological Survey. These less frequent and more violent storms are not ideal for groundwater recharge, keeping water as high in vertical elevation as possible in slow-moving or stagnant basins before allowing it to gather much kinetic energy and allow it to take out homes downstream. We need to keep that to a minimum, and especially erosion. Flash flooding is a characteristic of the Southwest, and this is due to climate change and a lot of other factors. Arizona cities are required to make progress by Arizona law on achieving 100 years worth of water availability. But the city of Phoenix is actively going against this by going 7% over their yearly allotted groundwater amountage. And this is as defined by the Arizona Department of Water Resources. And they say with this trend, we will be a water-stressed state by 2040. Think of water-stricken California with bans on washing your own car in your driveway, and you cannot have water brought to you in restaurants because they don't have any water for you. So.
So the technology we're using, what part of it is calculating groundwater recharge? That is currently an issue for researchers. There's an immense amount of data that needs to be calculated and sometimes these calculations need to be on a per acre basis. And to solve this problem, this is where AI comes in. Large language models such as explainable and adaptive network-based fuzzy interface system, or ANFIS. These AIs can do the mathematical work by calculating thousands of acres of land, only need to be supplied with information from the Geographic Information System, or GIS. That includes the depth of a rock, how much rain a place gets, and extracts this information from thousands of data points across the country. Assured Water Supply, or AWS, of 100 years, shows 100 years of normal withdrawal during a major drought. And then we can think of this as a bank account. For example, we have the state of Arizona has a budget of $1 million gallons of water. If tomorrow you have to rely on that, if you lost your job and say you have to rely on that bank account for the next 100 years, this might not be a sustainable spending rate. So our sources include one talking about how artificial groundwater recharge locations are identified more easily with AI, and how AI looks at GIS data and is incredibly accurate. These sources reflect the view of researchers in this field that AI expedites the process of calculating groundwater recharge variables. And these tests over hundreds of thousands of acres of land show that possibility of groundwater recharge can be found through factors related to GIS data. And as previously mentioned, this process relies on a large language model and adding various points of data which will be scattered across the country. This is significant, as before AI could do this or even computers existed, this all had to be done by hand, making the process much more complicated and time consuming. Also, additionally, since AI has a much higher accuracy than people, it reduces the margin of errors. It can also track nearby samples to make sure data is being tracked correctly.
And then there are some issues with this technology. So this is Zong presented a literature review study of the last 20 years and pointed out that climate change is going to be a really big issue. This is agreed upon by Al-Asari et al., especially measuring the decreased frequency and increased intensity of storms, which is something that we talked about earlier. And this is something that had to be implemented into our model. And then Zhang also agreed with Yang about the trouble with groundwater recharge in urban areas, which was a significant challenge we came to due to obstructions such as concrete and asphalt. That's usually these AI tests are performed in the middle of the desert or in the floodplains. This is not the case for our specific situation, and we had to review that.
All right, so what is our gap? So as we mentioned, this literature is not focused on the U.S. Instead, it's focused on areas such as the Middle East and countries like Iran and where there's a lot more arid and urban areas with the near, like previously mentioned, use a ton of concrete and asphalt and are usually understudied due to these obstructions. There are some coefficients for Arizona density that are used, but site-specific ones such as GIS that aren't currently used would be helpful. And right now, Brophy and the Student Climate Coalition are working to achieve a safe yield, and we could be aided by more research as currently very little research on this topic exists. All right, so our research question: how could AI be used to evaluate Brophy's safe yield progress?
All right, so we used an AI model, Explainable, and this is a large language model, as mentioned earlier. It's we aggregated a ton of data. We can see rainfall, radiation, temperature, asphalt evaporation, and permeability. There's a difference between those two, and rock type permeability. And we surveyed every single every acre of Brophy's land. We did 18 tests, and we tracked each. There's very slight differences in the data per acre, and we worked on that, specifically relating to the asphalt permeability and the rock type permeability. So this is this test was run one time per acre with slight variations in the data, both averaged for the analysis later, and we allowed the AI to do the calculations with the provided formula. So we didn't just let it run wild with a bunch of data. Yeah. All right, so what we got from this. So withdrawal greatly outpaced replacement. So we have inflow, we see that it's closer to about a half an inch per year is actually entering the ground, as opposed to about 8 inches per year actually being rained on the Brophy campus. So it seems like the combination of just basically having so much concrete is taking that away from us. So the front lawn is utilized as a recharge, is the only thing that's utilized as a recharge basin, and this equates to actually very little recharge happening. Our model suggests that 5% of rainfall enters groundwater due to infrequent and low accumulation weather events. It is also due to the front lawn being the only groundwater recharge. And this means it would take more than 33 million acres of urban equivalent environment, which Brophy is analogous to recharge Brophy's yearly well water use. You can see on that slide, not including the watering of baseball field, front lawn, or Brophy's the sports campus. So this is exclusively within the parameters of the Brophy campus. It would take 18,000 Brophies to recharge the water that we use in 1 year.
All right, so right now there is no AI model for artificial urban recharge, and this is a severe limitation because evapotranspiration on different surfaces radically differs. Additionally, using the coefficient, which was used instead of potentially radar scanning, is not site-specific like other pieces of evidence we were able to collect. to fix this, we can, the further research can work on this implementation of a cone, of well research. And for future monitoring of safe yield, we can use the well water level as a baseline. And this well was used as an external source and was not relied upon by John, which our test emulated, but more specifically will be a data point that we could view at any time.
And then our sources.
Like, this is a touchscreen.
Yeah.